In this video, I want to focus on the Chapter 9 portion of the test review for 132. And what I'm doing is putting in just enough material to remind you that there's this, like, all these different categories of topics. For example, the couple fill in the blanks here. This first one is in reference to the idea that there's solute, solvent, unsaturated, and saturated solutions. The second one is dealing with the last section of Chapter 9, dealing with colloids versus suspensions. So I'm counting on you to go into those sections and review the material completely. So, like, for example, saturated versus unsaturated. That's where, well, let's just take a look. If a solid sample dissolves when it's added to a solution, it's just going to form an aqueous solution, and that's an unsaturated solution. Right, something that hasn't maxed out its solubility yet. When the solid doesn't dissolve anymore, that's when you have your saturated solution. Down here, we talked about these different categories of solutes in the last section. Simple salts are just typical solutions. Large molecules such as proteins, they form what's called colloids, or they are colloids. And the main criteria that we use to distinguish colloids from other types of solution is whether these items will pass through a semi-permeable membrane. And so if it can't pass through the semi-permeable membrane, then we classify that now as a colloid. And then a suspension would be that example where the particles are so large that they could actually be separated out just like with a regular filter paper. Whereas a protein's too small, it'll pass right through the filter paper. We discussed electrolytes, weak electrolytes, non-electrolytes in the context of the conductivity meter. And, the question is just asking which one's the brightest light. I'll do a little bit more than just that. Kind of to expand on the why part here. Well, just remember, when this light bulb glows brightly, that means that there are many ions in solution. So you have to get some ions in solution before you complete the electrical circuit. Now, just to deal with the easiest one here, this sucrose solution. So this is a molecular compound. It does not dissociate in solution. Right? For Chapter 9, we learned that salts are the only things that will dissociate. Chapter 10, we learned that acids will also dissociate, but they're not up here. So this is just a non-electrolyte. It produces no ions when it goes in solution. Therefore, there's no light produced. Whereas these two examples, both of them are, they're strong electrolytes because you're looking at soluble salts. Notice they're both at the same concentration. So on those two criteria, you would think they would generate the same amount of brightness in the conductivity meter. But what you have to appreciate here is that the calcium chloride actually produces a total of 3 ions in solution, whereas the sodium bromide only produces 2 ions. Let's just take a look at the formula real quick, or the equation real quick. So completely dissociating solution because it's a soluble salt. And notice I'm having to balance out the number of chlorides here. There's 2 in the formula. There are 2 in the formula there because calcium always has a +2 charge. So therefore, I have to have 2 chlorides to balance out the charge here. And now notice there's a total of 3 ions in the solution. Versus sodium bromide, when it dissociates, it only forms 2 ions. So this one will have a little bit less conductivity than the calcium chloride, 2 ions here. Now, realistically, with a conductivity meter such as the one that's shown in the picture here, it's not going to matter, okay? But if you had a more sensitive, like, I don't know, something that was actually measuring the current that's passing through the solution, it should be a way to distinguish between the greater conductivity of the 3 ions in solution versus the 2. Now, continue on the theme of solubility, we also had these, the solubility information. Specifically, like, actually, we can just use this first one to illustrate what I'm thinking about. If we want to know the solubility of potassium iodine at 60 degrees on this table, you're just going up, and I've picked potassium iodine because it's at the top of the list here. Right? What is the concentration of the solution at that point on the graph? Now, this graph there's not high degree of resolution on this. I'm just going to say about 170 grams of potassium iodine in 100 grams of water. Right, that's the maximum amount of salt, of the solute, that can dissolve in that amount of water. It's solubility. what I have to appreciate here, one other thing, I mean, that's the answer to that question, yes, but just like many times in these test reviews, I'm going to use this to sort of expand on the idea. But if I focus in on just the potassium iodine line here, right, as I'm marching up and I'm adding more and more potassium iodine into the solution, right, everything's going to dissolve down here, and we call that, just like that first question that we did a few seconds ago, that's an unsaturated solution. Right? You have not maxed out the solubility. As soon as you get on that line, you've maxed out the solubility, and then anything above it, you're going to say is a saturated solution. And in a saturated solution, a solid is going to persist in the solution. Part B is kind of asking, dealing with the same topic. Here, we're talking about boiling water, so we're over all the way out to 100 degrees Celsius. We're dealing with sodium chloride. Notice its solubility is pretty flat on the chart. And the scenario, well, what's going to happen if I try to add 45 grams to 100 grams of boiling water? And again, watch that value, right? I can compare this directly what's on the graph. I don't have to do any math to adjust the proportion, which I'll have to do down here. If I go up, I see that the solubility crosses at about 40 grams per milliliter. So that 45 is above the line. Well, what happens above any of these lines? Well, that's a saturated solution. So the answer to this is that, well, no. Some solid would remain. And actually, it's about 5 grams of solid would remain, because we call this a saturated solution. Now, the last one here, we're going to have to do a little bit of math, because we're wanting to know the amount of glucose, and there's glucose. Glucose is on the list there. Actually, let me change. Different color. That's not showing up on that background too well. Okay, so we're dealing with 40 degrees Celsius, so we're on this vertical portion, and we want to know if we're going to form a saturated solution, or actually I should say how much glucose is needed, do we need to add to 25 grams of water to form a saturated solution? Well, the amount of water here, 25, that is not in agreement with the 100 grams of water, so I'm going to have to adjust the proportion on this one. First thing I need to know the solubility of the glucose at 40 degrees, and just reading off the chart here, it's coming in about right there, so I'm going to say it's about about 130 grams here. So the solubility of glucose, saying that 130 grams of glucose will dissolve into 100 grams of water. Okay, great. How much water do I have? I have 25 grams of water. I want to know the mass of the glucose that will dissolve in it. That's where our X is in this example. Now, there's two different ways you can approach this. The cross multiply divide will work just fine. Remember, that's do it this way. We saw it in the notes for Part B of Lab 15. I did an example of the cross multiply and divide, if you want to check that out. And the X value, if I did this, would be equal to, let's see, 32.5. 32.5 grams of glucose can dissolve in that 25 grams of water. So that's one way to do it. Another way to do it, sometimes the numbers work out in your favor. Like, for example, 100 is a multiple of 25. Right? So if you think about how this math was done, what do you have to do to 100 to get to 25? Well, you would divide by 4. What is a proportion? A proportion is just, trying to keep the ratio between, in this case, the grams of glucose and grams of water equal. So whatever I do on one side to get it down to the lower ratio, I can do to the other end of things. So, if you have, again, a set of numbers that are multiples of each other, and you can figure out what you've divided or multiplied by, depending on which way you're moving in the calculation, then you can do the same math to the in this case, the numerator. So 130 divided by 4 will give you the 32.5. Now, in this particular problem, the formatting was just off. Okay, and so there's a figure here that's missing. What this question is trying to get at is it's asking you to imagine that you have two sides of a chamber, and it's separated with a some kind of membrane. Okay, and the membrane allows water to pass, almost like a biological membrane that's very selective in terms of, like ions and molecules that it's going to allow to pass. So you have these two sides across the membrane. Which way will water move? Okay. What you have to remember here, and this is associated with last section of the chapter when we do the hemolysis and chronation, isotonic, hypotonic, all those different terms. Basically, what we learn there is that water, and I'll just put that up as the answer here, the explanation, or part of it anyway, water moves toward the higher concentration. It's basically osmosis. It's sort of the driving force of all this. So once you realize that, these problems boil down to a fairly simple kind of approach, okay? For example, this is a higher concentration. The water is going to move toward which side rises. Well, if the water moves toward this side of the chamber, then the water level of B is going to rise. Here you have two solutions. The concentration is the same. The degree of ionization is the same, meaning when sodium chloride dissolves, it forms two ions. When sodium iodine dissolves, it forms two ions. As it turns out, there's no movement, so neither side rises. And then down here, it's actually in reference to what we were doing right up here. So calcium chloride generates 3 ions versus, well, sodium bromide or sodium chloride. That's the 1-to-1 ratio of the ions here. They're just going to produce 2 ions. Because really, I mean, the driving force of the water moving back and forth across the membrane is really a function of how many particles are in the solution. So here, what you have is, the concentration may be listed as the same, but once it dissociates, there's more particles or more ions on this side. So the water will tend to go into that direction. So it's the A side that's going to rise with that example. Now, the full key to this one is posted on Moodle, so I'm not going to do all 3 of them. I'll do bits and pieces of each, and then one, I will take the time and actually go through these different equations, all right? Like, for example, if you look at silver nitrate and the lithium sulfate, if you check out and do like the double replacement reaction for this set of solutions, you get silver sulfate and lithium nitrate as your 2 products. Well, as it turns out, if you check the solubility table, you find that both of them are soluble. Now, remember, I gave you a short list. Again, it's Lab 15, Part A video there. There's a short list of ions to know about this. And actually, it's in that video that I also do this breakout of the different equations. But we learned in that video that any kind of nitrate or sodium or lithium salt, acetate ammonium, potassium is the other one, any of those salts are going to be soluble. Okay, so they're always going to form an aqueous solution. For the silver sulfate, then you would have to have a solubility table to figure it out. Okay, and what you would find is that this is an aqueous solution. This is a soluble salt. So in this reaction here, well, in this question, it's no reaction. So you don't have to complete anything, really. Right here, what we're going to see, again, if we do the double replacement reaction, on one end we get the sodium nitrate, and then on the other end we get the copper carbonate. And what I want you to realize here is that the copper is actually coming in at a +1 state, and the way I know that is because I know nitrate has a -1 charge. And in the ratio of the salt formula, I see they're coming in at a 1-to-1 ratio. So that means that the charge on the 2 ions have to be equal and opposite. So since nitrate's always -1, then this particular copper is going to be +1. Carbonate always forms a -2 charge. So I have to bump up the number of copper cations so that I can balance out the -2 charge there on the carbonate. So that's why you see a 2 sitting there. Now, again, there's our nitrate salt. This one's going to be aqueous. And if we look at a solubility table, what we find is that, well, most salts of carbonate are insoluble, except for a few. Copper's not on that list. So this one is going to form a solid. And it's actually this one that I'm going to do for our reactions down here. And I'll do that in just a minute. And then finally, well, actually, a cation, the anion here, it forms, well, surprise. Nitrate and sodium salts are incredibly common in these kind of reactions, so it's not unusual to see this kind of pattern. It's the other one here that's actually going to form our insoluble salt. And lead is taking on a +2 state. Sulfate always takes on a -2, and so these two are going to come together in a 1-to-1 ratio. And again, most salts of sulfate, typically soluble. Lead is an exception. It's insoluble when it bonds up with sulfate. Again, the one that I want to work through, though, is B. Now, I already have the beginnings of the molecular equation. Let me rewrite everything to have it on a single line here. And remember, when we do our molecular equations, all of these equations, we'll want to add the phases, the correct phases in. And so since I'm adding solutions, they're all aqueous, so I get the AQ tag. I know a solid forms here, so I'm going to use my S phase, solid phase for it. and then wrapping up with the sodium nitrate. And it's also aqueous. What I want to pay attention to here are the number of ions in each. So, like for example, I have 2 sodiums over here and only 1 sodium here, so I need to put a 2 in front. Remember, once you get the salt formulas in place, like this is a 1-to-1 ratio, this is a 2-to-1 ratio, I don't go in and I don't tweak subscripts anymore. If I'm trying to balance the overall equation, I can only change the molar coefficients in front there. And then notice what happens here. The nitrate now comes out of balance. I have 2 nitrates total here, only 1 here. I need to put a 2 in front there. And then the last thing, what happens is that since I got 2 coppers due to the adjustment of the molar coefficient here, it balances out the 2 that's in the original salt formula. It's fairly typical. If you get your molecular formulas correct, which I have, then usually within a few little steps you've balanced the equation. If you're in a situation where the numbers, if you're constantly like erasing and changing the numbers of the molar coefficients, what that probably means is you made an error in one of your molecular formulas, and you should go back and check the charges, make sure you have the ratio correct. Okay. Now, the ionic equation, that is the one that is most busy, okay? So what I always recommend doing is just balancing the molecular equation first, and then just reading it across one at a time, and then, translating that down here. And the main thing you're doing is being careful and not to being careful. If it's an AQ, you're gonna break everything up. Now remember, when an aqueous solution forms, any individual ions in the formula are going to break apart into free-floating ions. So that means that the 2 does not stay as a subscript. That would imply a diatomic ion, and sodium does not do that. Instead, it's 2 free-floating sodium cations in solution. And then you got carbonate, which is also aqueous. And again, just take it one at a time. Right? You're also factoring the molar coefficient that's in front. Right? And that 2 affects not just the cation, but also the anion. And then the only molecular formula that stays together is the solid. Okay, so this one is going to, right, that's accounting for the observation that we would have made. Solid forms, there's a reaction right there. And then I'm going to have to squeeze this in. But again, I do the same thing like I did on the reactant side. If I see an aqueous solution, then I'm going to break everything apart. If you have this molecular equation balanced correctly the first time, and you apply your molar coefficients correctly, then everything here is going to be balanced as well. For example, 2 nitrates, 2 sodiums, 2 nitrates, 2 sodiums, 2 coppers there. Okay, so everything's nice and balanced. I didn't have to, since I used this, I didn't have to go back and really check any of my work on the ionic equation. Going to the net ionic equation, what you're trying to do here is you're kind of trying to account for the observation. The observation is that 2 aqueous solutions were mixed together in a solid form. Well, how did that solid form? Well, it's formed from a combination of those 2 ions going to this salt. And it doesn't matter which one you write out first. Again, factoring in bringing the proper molar coefficients down, because, right, you have to have 2 of those copper cations to balance out that -2 charge on the carbonate. What's happening to the sodium and the nitrate? Well, they don't change in any way. They started out floating free in solution, they stop. They end up floating free in the solution. They're spectator ions in this example. Sodium and nitrate will always be spectator ions in precipitation reactions. And then the last problem for chapter 9 is this one. We want to calculate the molarity. So you'll have the equation for molarity on the test. You want moles per liter. Okay, so a couple problems here. One, when I look at the data that's given to me for this glucose, I don't have the number of moles. So we did that in class. We're going to do a mass to mole conversion as well here. And then the other part is that I need the milliliters in liters. Let's do this one real quick. Right, we need to remember that there are 1,000 milliliters in 1 liter. So when you do this type of calculation, actually I'm going to, when you do this type of calculation, you're essentially moving the decimal over 3 places, dividing by 1,000. And I'm going to do proper sig fix here. That 0, with the data that's given, that 0 is not significant because there's no decimal there. And so really, that 0 would not be used in the calculation. Let's just go ahead and ink that in. Okay, so we have just over half a liter. And now let's take this information and calculate the number of moles. So one thing you have to do is you have to figure out what the molar mass is for the glucose. So if you take, well, let me just write this out. Why not? So we have carbon, hydrogen, oxygen. The molecular formula is 6, 12, and 6. To get the molar mass, what I do is I multiply for each atom of the particular element, in this case 6 for carbon, I multiply it by the atomic mass that's on the periodic table. Do the same for hydrogen, do the same for, and do the same for oxygen there. And so this comes out at 72.06, and I'm leaving off the unit because I'm sort of run out of space, 12.12, and then this is 96. And typically when I'm doing the molar mass calculation, I always use 2 decimal places on the atomic number. Add this together and I get 180.18, and the unit here, finally, is grams per mole. And I'm going to use that in my calculation. So let me try to squeeze it in right here. Do I multiply by, do I divide by this number? Well, my goal is to cancel out grams. 100, you can think about it this way. If I go in the laboratory and I weigh out 180.18 grams of glucose, I'm going to have approximately 1 mole of that sample in front of me. This makes it look like a conversion factor, which it is. And we learn with the conversion factors, whatever unit that you want to get rid of, it's that portion of that conversion factor that's going to go on the bottom. So in this case, you're going to divide by the 180.18. And by doing that, right, the grams cancel out, you're left with moles, and the value is 0.416 moles. And we're going to insert that up here, and you're ready for the final calculation. And that's simply just dividing the 2, and then notice we've got 2 sig figs here, and so the final answer needs to come in at 2 sig figs. Now my calculator is going to give me that value. Right? I want to keep 2 sig figs, so the next digit down, well, 5 or above, then you round up. And so the answer would be reported as that. So 0.76 molar. And I'll have separate videos for chapter 10, chapter 5. Okay, thanks.